Good morning, everyone. Um, Apologies for the late start. I would like to welcome you all to this event. We have students coming from different parts of Africa, as well as mentors from different parts of Africa to this maiden edition of the Quantum Hackathon at AIMS. And I am excited to see a lot of our speakers and judges who have traveled from very far away and near to grace this occasion. And let me say that there are a lot of exciting prizes to be won by the teams of the hackathon. And I can see that everyone is fired up for the program. Let me start by saying that the emergence of quantum science and technology represents a new frontier which many believe will drive the next global super cycle of innovation and sustainable industrial growth. This year, the UN declared this year as the International Year of Quantum Science and Technology, following 100 years since the discovery of quantum theory. As part of the celebration, AIMS put together 3-in-1 events, which we start today. The first one is the Quantum Hackathon, also known as the Quantathon. This event is organized in partnership with the Open Quantum Institute as part of the Hackathon in a Box series that was started by the OQI. And we are pleased to say that this is the first time the event is happening in Africa, and we are proud to be organizing this event at AIMS. In parallel to this is a quantum technology education workshop. So while all these experts are here to give you feedback on your project and also assess it at the end of the day, we also want them to sit together and discuss how to build capacity for quantum technology education, especially for the Global South. So we will be having a quantum technology education workshop that also starts this afternoon and runs till tomorrow. And then on Friday, there will be a public lecture at the University of Ghana CD Conference Center. Before I Before I proceed, I want to say a big thank you to all our partners. I started by saying that this is thanks to the support of the Open Quantum Institute, which was formed out of JESDA, and also supported by the MasterCard Foundation, a scholars program at AIMS. We have a lot of partners. The International Year of Quantum, UNESCO, CERN, Google, Imperial, IBM, Q-Braid, NYU Abu Dhabi Hackathon. Q-World has been very supportive in training our students. We are also partnering with the Ministry of Science and Technology the Ministry of Education in Ghana, and the Ghana Academy of Arts and Sciences. Other partners include QSoft and Quantum Delta NL. We have, for the hackathon, we have a lot of prizes, amazing prizes. Students have opportunities for internships in quantum technology companies across the globe. We also have exciting prizes for the winners, huge prizes. I'm not going to announce it now, but I can tell you that it's huge. And I encourage you to work hard and be determined to win. Before I take my seat, I want to acknowledge our speakers and judges who have traveled from very far to come to this place. I'll just mention their names. We all know them. We have seen their pictures, but we haven't seen them in person. So I want to start with Jonathan. Jonathan Oppenheim. So Jonathan will be giving the public lecture on Friday, and we are very pleased for you to come. And then Mighty. So Jonathan is from University College London. Mighty is the Director for Training at the Perimeter Institute. Director for Training and Outreach at the Perimeter Institute. Karen is a superstar. So and well known for advocating and advancing quantum theory. She came all the way from Argentina. I have been with her on the World Economic Forum Global Council for the Future of Quantum Technology. Thank you for coming. Marcelo. Marcelo came all the way from Brazil. So we are very pleased to have you. Ian Wormsley is the provost for Imperial College, and he is our keynote speaker for today. He will be giving us an amazing talk later today. Philip. Some of the students may recognize you. So he's already taught a class in quantum information processing at AIMS recently, and from the OQI, and he will be telling us a lot more today about quantum technology use cases after my talk. So thank you for coming. Sandro is a special advisor to JESDA. And Stephanie is, okay. and Melody is from UNESCO, responsible for science. Thank you for coming. So we have all these distinguished speakers. Some of them are going to be, in fact, all of them, almost all of them are going to be judges as well. And they will be coming to your, visiting your groups and giving you feedback whilst you prepare for your presentation. So once again, I want to say a big congratulations to all the team and all the organizers who have made this happen. And thank you very much.
Thank you so much, Prince, for this introduction. My name is Philip Kamelander. I'm happy to give you a quick introduction to the Open Quantum Institute and what we do at the Open Quantum Institute, and in particular also present you one of our use cases that we're working on. Before I start, I'd like to thank sincerely Prince and everyone in the organizing team for making this series of events possible. I think it's great to be here, also great to be back actually and see so many familiar faces. Very good to see you, and I'm very happy to be back in Accra. So it's inspiring to see so much talent and so much energy in the students' faces, as I've already seen in February at AIMS and again today. And I think as we gather here today, and in particular for the hackathon, it's not just about coding and about competing, but it's also about purpose. What I mean by that is that the theme of this hackathon challenges us to think big, to ask ourselves, how can quantum computing, an emergent technology with great promise, can add to achieving the Sustainable Development Goals of the UN? Today, it may be a bit early to hope for quantum advantage, in particular in this context, but the hope is alive that at some point in the future this will happen. And this is your challenge at this hackathon, to ideate and to find hopefully new ideas, to innovate, and in the end also to present your ideas. Yes, can we have the slides maybe? Let's give it a minute, maybe. Thank you so much. Great. So, the reason why I was asking for this slide in particular now for the next point that I'm making is that what we are asking you students, to do at this hackathon is very much in line with what the Open Quantum Institute is doing. And in order for you to understand a bit better where the Open Quantum Institute comes from, I would like to spend a few minutes introducing the journey of OQI up to today, our plans, what we do, and then in particular focus on what we do and what's the connection to this hackathon and to the use cases development. So the Open Quantum Institute was conceived by GESTA, the Geneva Science and Diplomacy Anticipator, and I'd like to quickly introduce you to the idea of GESTA. Next slide, please. So that's a GESTA is an instrument of anticipation. It's a do tank rather than a think tank, and it's favoring public-private partnerships of international scope. As such, it wants to anticipate, to accelerate, and to translate. In particular, anticipate scientific breakthroughs and accelerate the development of solution ideas to tackle global challenges, and then, in the end, translating these opportunities into action. Next slide, please. The slogan of GESTA is use the future to build the present. So what has been done at GESTA in the past few years regarding the Open Quantum Institute in particular is to think of how could the future look and how can we anticipate, start to anticipate today. And in particular, when it comes to quantum computing, which is a technology of great transformative capability, one thing that is very important in this context is to make sure that there is equitable access to quantum computing for everyone on this planet, and to make sure that also this technology is used for the progress of the benefit of humanity. And this is why GESTA conceived the Open Quantum Institute. Again, anticipation, acceleration, and now translation of these opportunities into action. Next slide, please. So the journey of the Open Quantum Institute has been as follows. As I said, GESTA designed it and also incubated it with a public announcement in 2022. And today, as we speak of today, we are in the middle of the pilot phase, and I think it's fair to say really in the middle. So the pilot phase is 3 years, and it started in the beginning of 2024. And in its pilot phase, OQI is now hosted at CERN in Geneva, supported by UBS, and still also heavily involved is, of course, JESTA. So this is what we are in now. Next slide, please. And the Open Quantum Institute, as I said, is JESTA's answer to anticipation, acceleration, translation, in the sense that it is a multilateral governance initiative bringing together various players to promote global and inclusive access to quantum computing, and in particular its applications for the benefit of humanity. So this all sounds great. Now let's come down to earth and think about what is actually being done at the Open Quantum Institute. Next slide, please. So there are 4 strategic pillars of the Open Quantum Institute, and I'd like to say a few words about all of them, about some a bit more, about some a bit less. There is A1, accelerating applications for humanities. A2, access for all. A3, advancing capacity building. And A4, multilateral governance for the SDGs. I'm going counterclockwise. No, please go back to the last slide. I'm going counterclockwise, starting with A4. So A4 is really about multilateral governance for the SDGs, and in particular, the goal is to engage diplomatic players, also through discussions and raising awareness. So there are more than 20 permanent representatives involved, based in Geneva and all across the world, also in country. So that is A4. Now to A3, next slide please. A3, advancing capacity building. This is, I would say, the main reason why we are all gathering here today. So this is about educating students, but not only students, also other stakeholders in the world in quantum computing. Next slide please. And in the A3, advancing capacity building, there are several actions that the Open Quantum Institute is involved in. So there is an educational consortium of more than 55 people trying to curate and collect resources that are made available online for everyone to learn about quantum computing. There are more than 80 experts involved, actually in total, and more than 55 institutions. So excuse me about the messing up the numbers. Then another action is the Quantum Hackathon that Prince mentioned, which is the type of hackathon that is happening in the coming 3 days. So that's going to be exciting. The idea is to think about quantum computing use cases that are related to a sustainable development goal. That's the challenge that you will be faced with. There is also other actions like the quantum diplomacy game, and also a heavy involvement in the International Year of Quantum Science and Technology that Prince already mentioned. So in 2025, next slide please. In 2025, there is a series of hackathons happening all across the globe. As Prince highlighted, the one in Ghana is the first one in Africa. So congrats on that. That's great. To some extent, it's also the first one happening that was happening thanks to OQI. It's not the first one exactly, because there was also the one in Abu Dhabi, the UAE, but that's a hackathon that has already existed for some time and has been developed and is now also part of the OQI hackathon series. So this is the first one that only exists thanks to OQI. So that's another great achievement. And you see there is a number of other hackathons happening in 2025, and even more so in 2026, and hopefully also beyond. So that is what OQI is doing in the strategic pillar of A3, advancing capacity building. Now coming to A1. A1 is about accelerating applications for humanity. Next slide, please. So this is what I'm personally most involved in as a partner of OQI. And let me maybe quickly say a bit about what's the challenge here, because what A1 is doing on the large scale is to some extent what you're doing here in the hackathon on a potentially smaller scale. So A1 is trying to come up together with international teams, with use cases of quantum computing that help achieve and find solutions to the United Nations Sustainable Development Goals. What you see here is a map of the world with countries highlighted that contribute to these quantum computing use cases that we're working on. So we try to be global, but you see it's still very Europe-centric, so we try to work on this heavily, and we will hopefully do a lot better by next and the year beyond. So what's the challenge is actually twofold in my interpretation, and both parts of the challenge are extremely hard in their own right. So first, what you need to try to do is you realize, okay, there is a real world problem that is connected to a sustainable development goal, and one needs to connect this to a computational problem that could potentially be solved, okay? So the connection from a real world problem to a computational problem in itself is already quite tricky to make on solid grounds to do this properly. But then we are not just looking at computational problems. What we try to look at is computational problems that are connected to quantum computers potentially offering some type of advantage. Could be an advantage in terms of a speed up, it could be an advantage in terms of higher accuracy, or it could be an advantage in terms of less energy consumption for the computation, or maybe some other type of advantage. So the second part is to connect your computational problem to a potential quantum computing solution. So essentially some algorithmic ideas that are that work on quantum computers and hopefully offer an advantage, which again is a very difficult problem, maybe even the more difficult one. So these two challenges is what we work on, and for doing this we try to partner with institutions, academic, industry, NGOs, UN organizations, private persons all over the world, and try to build powerful interdisciplinary teams that try to solve both challenges at the same time. That is what accelerating applications for humanity is at the Open Quantum Institute. In the last few minutes, I would like to show you a bit about what this means in practice. I would like to show you one of the use cases that we are working on together with a team from France, Belgium, and Switzerland, together with a company called Pascal based in Paris. I hope the slides are coming back in a second. Maybe I can use this time to comment quickly on the fourth pillar that I have not mentioned yet, which is A2, access for all. Of course, having quantum computing solutions at some day for SDGs, Sustainable Development Goals, is good, but in order to deploy them, one also needs access to the quantum computers, to the quantum devices. So that is what A2 is about. This is about partnering with numerous industry providers, but also academic institutions, high-performance computing clusters, to make sure that also the access to the hardware is there. And hardware can mean access to quantum computing, but also it can mean access to quantum simulators, or typically it means hybrid access to both high-performance clusters that can also delegate some of the tasks to quantum computers. Okay, how are we doing with the slides? I can start with an introduction, hoping that the slides are coming back in a minute. So let me now focus the last few minutes on one particular use case that the Open Quantum Institute is working on. This use case is connected to essentially very complicated systems of water pipe systems in big cities with thousands of junctions and thousands of pipes that need to be monitored in order not to lose too much water. Depending on the season and also on the region, it can happen that up to 50% of fresh water is lost in cities due to leaks in these water pipe systems. And here we're talking about huge systems and huge cities. And the question that people try to answer is, how can we optimally place a very small number of sensors supervising the pipes and the junctions in order to detect leaks as early as possible and hopefully fix them before too much water gets lost. This is a problem that is essentially mathematically called a graph problem. Okay, so you have this graph of junctions and pipes. A junction is a vertex and a pipe is an edge. And you ask yourself, on which junctions would you like to place sensors? You have only a limited number of sensors. And on which would you like to place them so that you detect, so you prevent as much loss as possible. Okay. This graph problem is connected to what is called the maximum weighted independent set problem. So now maximum independent set, MIS, is a well-known graph problem. And now this graph is not just an arbitrary graph, but it's a weighted graph, because depending on how much water flows through each pipe or junction, or how high the pressure is, exactly, thank you, how high the pressure is, one can of course add a higher weight to certain pipes and junctions than to others. Okay. So as I said, the team is comprised of Reply and QClavis, as well as Pascal, and also supported by UN Habitat, the UN organization that validates and also heavily supports the development of this use case. As I said, the idea is to find an optimal placement of sensors in the pipe network, which improves the identification of damaged pipes, and therefore the ability to fix and replace leaking pipes, and hopefully therefore decreasing unaccounted for water, which is adding to SDG 6, clean water and sanitation. That's the idea. Next slide, please. So what I like about this use case is that it's very, very, well, easy to grasp the problem, not so easy to find the solution in general. So what you see on the lower left is a toy model of one of these graphs. Okay, so you see the junctions and the pipes, and here the coloring is giving the weight. So the red vertices have a high weight, while the blue vertices have a low weight, and this may depend on several indicators, like, as I said, pressure, water flow, how many pipes are coming together, and so on. And what's nice about these types of graph problems is that there is potential for what is called a neutral atom quantum computer to natively solve such graph problems on a large scale. Today we are not there yet, but there is hope that this will happen at some point in the coming years. And in these neutral atom quantum computers, a node in the graph, so a junction, is represented by an atom, and the vertex in the graph is represented by two atoms being close, and if there is no vertex, the two atoms need to be far apart. So two atoms being close means they interact, two atoms being far apart means they don't interact. So this is what this water leak detection use case is working on, and the team is actually currently getting ready to both simulate this on the quantum simulators and emulators, but also getting ready to have a first implementation on actual quantum processing units from Pascal in this Paris-based company that I mentioned before. So this is one example of a quantum computing use case that is related to an SDG. And you saw that there is quite, even in these 2 minutes or 3 minutes introductions that I gave, there is quite a lot of arguing to be done in order to connect the original problem of water loss to the mathematical problem and then to a potential quantum solution. And I've only scratched the surface here. So there's a lot to be done. And this is what many of you will today, tomorrow, and the day after tomorrow work on. And I'm very excited to see many ideas, many other ideas than this one. This is just one example. So many other ideas on SDG use cases of quantum computing. And I wish you a lot of fun, sleepless nights, and yeah. And I hope to see great ideas by tomorrow and Thursday. Thank you so much. Looking forward to the coming 3 days.
Good morning, everyone. My name is Melody Esiawonamboateng, and I'm the National Professional Officer for UNESCO's, or in charge of UNESCO's science sector programs here in Ghana. It's a pleasure to be here. It's actually an honor to be here. And so I will start on all the existing protocols to acknowledge all you wonderful experts, our dear students who are gathered in this place, and also to say a big congratulations to AIMS Ghana for putting this together. In actual fact, the first time that I heard anybody speak about quantum science or quantum technology or quantum computing was like 3 years ago, right, Prince? My director and I paid a courtesy visit to AIMS office, and Prince brought the issue up. And in order not to display my ignorance, I sat quietly and I listened. And I kept asking myself, wow, so there's something like this that could, you know, solve a lot of our problems in a short turnover, you know, a short space of time. So why aren't we investing in this? That was, the thoughts that kept coming to mind. And my director told Prince that this is a wonderful thing, and we commended him for already envisioning that Africa should not be left behind when it comes to this technological wave. We should be part of it. And in discussions with one of the experts seated by me, he also mentioned that it's not only about Africa being part of it, but also contributing to it, being a player when it comes to quantum science, quantum technology, and quantum computing. So it's indeed an honor to be here. And I was asked to talk about sustainability or the Sustainable Development Goals, and I chose to title my talk today, Quantum Futures and the Sustainable Development Goals, Bridging Science, Education, and Equity. So since I've been asked to focus on the SDGs, I'd like to introduce us to the SDGs. I know a lot of you know about the SDGs, so I won't go into details. But I would start by touching on the fact that the SDGs are a global framework or a call to action. And the key word here that you should take note of is action. It's not an inspiration. It's not something we are aspiring to. We want to act on it. And what do we want to do? It's to end poverty, protect the planet, and ensure prosperity for all by 2030. The SDGs, as we know it, was adopted in 2015 by all 193 UN member states. It is made up of 17 interlinked goals, each with specific targets and indicators. And before the SDGs, there was the MDGs, the Millennium Development Goals, which was implemented from 2000 to 2015. And the SDGs, we believe, builds upon the success and lessons from the Millennium Development Goals. And one of the things that the MDGs looked at, the Millennium Development Goals, was that it was mainly focused on developing countries. And the target was to address social issues like health and education. Whereas the SDGs is global. It concerns all of us. And then it also highlights the issue of partnerships. And then at the center of the SDGs is the issue of sustainability, which we shouldn't lose sight of. So as I already mentioned, the SDGs are made up of 17 interconnected goals for development. These goals are inclusive, they are equitable, or they seek to achieve equity in every aspect of society. And then the goals also aim at being environmentally sound. In other words, anything at all that we do under the SDGs, we should maintain, or we should bear in mind that it should not impact the environment negatively, any intervention whatsoever. As I mentioned earlier on, the focus is on sustainability, economic growth, innovation, global partnerships. And since this is a talk, I'm going to ask, and do not refer to what is on the screen. Which of you would be able to tell me what sustainability is? Sustainability, I'm sure you've read a lot. Sustainability, in your own words. It doesn't have to be defined verbatim as the UN or other agencies officially defines it. Great, thank you. Self-propelling. Self-propelling. Any other word that comes to mind? Sustainability. Okay, so basically, it's to ensure that whatever we are doing, whatever aspirations we have, whatever steps we take to be able to attain our goals, our aspirations, our interest or drive, we should ensure that we do not deny future generations of their opportunities. So basically, that is what sustainability talks about. And that is the fulcrum of the SDGs. That is what the SDGs is built upon. And I believe that you all will side with me when I say that currently the trends of development that a lot of us are, or a lot of countries are pursuing is not sustainable. The trends in business, fast fashion, fast food, fast that, fast this, it's not sustainable, which is why the SDGs have become even more critical, and we need to focus on it. We need to put all the resources that we have to back the attainment of the SDGs. The other thing which makes the SDGs matter now also is the fact that we only have 5 years left to attain this goal. I mentioned earlier on that the member states, or all nations, all countries, came together to agree on the SDGs and to start its implementation in 2015. And the end point is 2030. We are in 2025 now. In other words, we don't have time at all. We need to work hard. We need to work together. We need to move fast because we only have 5 years. And how do we move fast? Science and technology, countries, experts, researchers, those of you here, I'm sure you've all come to the realization that we need science and technology to accelerate the SDGs. What have I learned in recent times by reading that quantum tech could impact or contribute to sustainability? First and foremost, in one of my readings, I found out that quantum technologies can revolutionize sectors such as energy, the energy sector, climate modeling, secure communications, supporting sustainable development. And sustainability. Whenever we think of sustainability, we talk of issues like efficiency, optimization, and simplification of complex systems. And from what I've read, quantum science can help optimize supply chains, simulate complex systems, and enhance data. And these are critical keys to sustainable development. I've also read that when it comes to the issue of health, which is SDG 3, quantum science can support in an area called quantum sensing in medicine. It can also support in terms of finding sustainable or efficient materials for clean energy development. And then when it comes to climate, It's difficult to predict the climate these days. We are getting all kinds of, unpredictable heavy rains, droughts during unexpected times. But there is, research out there that proves that with quantum science or through quantum technology and quantum computing, climate modeling and forecasting can be done very well. And, the forecast would go closer to actual results on the ground. So these are some of the areas that I have learned and read that quantum science and quantum technology can support when it comes to the attainment of the SDGs. How are we doing, though, when it comes to capacity building? How are we doing as a continent, individual countries, and the whole world? And I'm saying the whole world because the SDGs look at everybody. It's not only about developing countries. It's also about the developed world. It's about all of us growing together. So how are we doing? We are not doing well at all. There's limited access to quantum education in Africa, which is why we need to laud the effort of AIMS Ghana, AIMS Global, for this workshop that is happening, because in a way, AIMS has democratized the opportunity. They've brought together you young ones, and I can see a good mix of both genders in this place to push you to go beyond your boundaries, your limits, in terms of your intellectual capacity to contribute to this, quantum science. So AIMS, let's give it up for AIMS. And all of these has direct links with SDG 4, that is quality education, SDG 9, and then 10. And I have this small bubble here saying that investing in education, relevant training, and infrastructure is crucial to ensuring equitable access to quantum technologies. Our shared mission, why are we here? The UN, UNESCO, we know that we can't do it alone. You young ones, you can't do it alone. The experts gathered here, no one country can do it alone. That is why this is a shared mission, it's a shared vision. There is a saying that if you want to go fast, you can go alone, but if you want to go far, you should go with like-minded people. We want the benefits of quantum technology to not only benefit generations of today, but future generations. And we can only do that through you young ones. That is why we are gathered here. And for me, I think the shared mission that we should all work towards is to ensure that we transform our education systems. I was having a chat with one of the experts this morning that in Ghana, there is a lot of goodwill and commitment that has been demonstrated by successive governments and ministries of education, ministries of science, or ministers of science towards science, technology, and innovation. But there's still there's more that needs to be done, especially in transforming our education systems. We know that science is the way, we know that technology and innovation is the way, but when you look at the numbers, and I'll keep using Ghana as an example, we still have more students in the humanities. So where can we flip it? How do we flip this? Other countries have done it. Yes, so please, it's a shared vision that we need to work towards. We also need to connect science to social good. Quantum technology, quantum science should benefit society. It's something that we need to work together. And last but not the least, foster quantum literacy at all levels. Prince, is that possible? Fostering it at all levels, from basic education to tertiary education. Prince says it's doable. So we will work on that. How do we make it happen? Let me quickly run through this. Princess, my time is almost done. We need to invest in education and training, support school outreach programs, create public-private partnership, align national tech SDG strategies. And we need policy to drive that. We need the right policies to drive all of that. And it all leads to greater SDG impact. So finally, I'd like to say that let's shape a sustainable quantum future together. Thank you all so much for your kind attention.
Hello, everyone. Good morning. Thank you to the organizers for having me here. Thank you. My name is Jennifer Hiable. I'm a PhD student at the Quantum Information Group at the Autonomous University of Barcelona in Spain. And today I want to talk to you about the geometry of absolute separability and related absolute convex sets. Okay, so I'll talk to you briefly about separability, and then I'll go over absolute separability, and then we'll talk a bit about geometry. So to start off, we know that in the space of quantum information, we have the class of quantum states. And in this class, we have two subclasses, which is the set of separable states, which have a more defined structure, and then the entangled states. And then we say that a state is separable if sorry for this, but we say that a state is separable if it can be written as a convex combination of products of pure states. Otherwise, it's entangled. Now, given a quantum state, to determine whether it's separable or entangled is a very hard problem, which is known as the separability problem. And this has been shown to be an NP-hard problem. Okay, so now what is most interesting is in the class of separable states, we can find a ball of radius 1 centered at the identity such that this ball is the largest possible ball you can find. Meaning that if I extend the radius of the ball even by a slight bit, we start to encounter entangled states. But what is most interesting is that the states in this ball are not just separable, but they are what we call absolute separable, meaning that they are resistant to global transformations or unitary transformations and do not produce any kind of entanglement even after the transformation. So mathematically, we say that if we apply unitary transformations or unitaries to the state, it remains separable. So the intrinsic property here means that the eigenvalues of the states preserve the separability of the states. So the goal of our project is to characterize separability via the eigenvalues of the states only. So that leads us to absolute separability. So it is just a property of the eigenvalues of a state. And then we define it to be, or we define a state to be absolutely separable if all quantum states with the same eigenvalues as our states are also separable. And in fact, this set of states are slightly larger than the ball. So there are some of the states that are absolutely separable outside of the ball, and we want to see how to characterize them. They do form a convex and compact set, so the geometry helps us to also understand them. So mathematically, we say that a state is absolutely separable if and only if the global transformation of a state remains separable. We can also define absolute convex sets. So if we take a closed convex cone M in the space of Hermitian matrices, we say that a set is absolute M set if every unitary transformation of the set, and if we take the intersection over all unitaries, we get that set, the absolute M set. We can also define the dual cone in a similar way, where we're just taking the sum of the unitary transformations of the dual of the cone, the original cone that we had. So for example, we can define absolute PPT sets as well. So here, a state is absolutely PPT if and only if the transformation of the state remains PPT. It's been conjectured, and we have numerical evidence to show that absolute separability is equal to absolute PPT. But this problem is very hard to solve, and we want to attempt to solve it. It's been shown to be true for qubit systems, but in higher dimensions, we don't know. So in general, I want to tell you a little bit about the geometry of the set. So we've seen that the set of absolute separable states and their dual are what is known as semi-algebraic in all arbitrary dimensions, meaning that we can express the set as a Boolean combination of polynomial inequalities. So I mean unions, intersections, complements, and so on. But more interestingly, when we consider low-dimensional absolute separable sets, they form what's known as a spectrohedron. And a spectrohedron is basically, if we take the intersection of the cone of positive semi-definite matrices, like you see here, and then we slice that with an affine linear subspace. So the spectrohedron is just the intersection of those two. It's unfortunate you cannot see the expression there. So here, on the right, we have the 2-qubit absolute separable spectrohedron. And on the left is its dual, which we call absolute separable witnesses. So in convexity theory, we know that the set of exposed points is contained in the set of extreme points, which are found on the boundary, and the boundaries contain the set. What we have found is that the extreme points occur at the points where we have states with eigenvalues, or at least 2 eigenvalues being equal. So if we look closely here, we see that we have 3 types of extreme points. Even though there are infinite number of them, they're categorized into 3. 3 curves which define these, defined by the equalities in the eigenvalues, at least in the qubit systems. Also, we know that every extreme point is exposed. So the set of extreme points and exposed points coincide with each other. So if we look closely, we see that a point is exposed if we can find a supporting hyperplane, so just a plane that when we intersect the plane with our set, we get back the point. So all the extreme points lie on these curves, and we can always find a supporting hyperplane which exposes them. We also know that the faces are defined by the null space of the defining matrix of the set. And here we have a face in the qubit system, which is defined by 2 eigenvalues which are proportional to each other. Also, we know that every face in the set of separable states, absolute separable states, at least in the low dimensions, are also exposed. So in general, we are still interested in the problem whether or not absolute separability is equal to absolute PPT. And the way we want to do this is to explore the facial dimensions of the set. We want to compare the two. We also want to know if we can find unexposed faces in a set of absolute separable states in the higher dimensions. So that's Q-Braid systems and above. And again, at the very least, we want to know if the set of absolute separable states is a spectrohedral shadow, which is just the projection of a spectrohedra across a linear map. And it's been shown already that the set of separable states do not form a spectrohedral shadow when the total dimension is greater than 6. So we want to check for this as well. So thank you very much, and this is my group.
Hi, everyone. Okay, so I have 5 minutes for this talk. I'm going to try to briefly describe everything that I've so far worked on. 5 minutes is a very short time to do this. My name is David Dosu. I'm Nigerian. I'm a research associate at CERN's Open Quantum Institute and a visiting lecturer at the University of Geneva in Switzerland. My background is in particle physics, advanced particle physics, beyond standard model. But we're not going to discuss, I'm not going to discuss any of that this morning. Instead, I'm going to focus on this. And if I'm successful with this talk, by the end of it, I think maybe 50% of the all will hate me and 50% would, I don't know, like me, which is fine in the end. But I'm in no way affiliated to Elon Musk. But we're doing something close to that here. So forecasting discovery, from bibliometrics to breakthrough. Please, the next slide. Oh, it's here. Sorry, let me check. For some reason, it's not. I think I'll have to call for it. Okay. All right, so what can well digging in Africa tell us of randomness? So one thing we understand is that, I don't know if this is something that is still in existence here, but say 10, 20 years ago, there used to be a lot of digging of wells. And in fact, when these things had to be dug, so this is not what it looks like. This is sort of like a borehole. Wells are the round one where you have to use like a rope and to fetch water from it. But what we understand is that if you go back, say 10, 20 years ago, the digging of this thing used to be super random. So what you have is like you gather lots of people, and you take them that, okay, we're going to dig for wells and something, and you dig, and sometimes you find water, and that is good, and if you don't find, you have to cover it up back, and you do it all over again. But I think of this in terms of the Bayesian parameters. So what are the parameters that, but because of some technological breakthroughs, that changed by a lot, right? So it used to be super random, but then we discovered geophysical surveys and the technology behind it. The UNESCO and some other organizations joined in this thing too. And exactly because of that, I think it shot up from like 49%. And if you have 49%, that means we don't know. It shot up from 49% to like 92. So now we can tell with accurate precision before going to dig a well that we're going to find water in this place. So that happened. But what are the Bayesian parameters that we considered to do that? So we have the introduction of manual drilling, we have geophysical surveys and technology, we have policy and infrastructure support. Now, the one thing that is peculiar in this thing is that science is still being done this way. Please, the next slide. So science is still function this way. Researchers and sciences is still like looking for needle in a haystack problem, right? So what if we can figure out the Bayesian parameters that is needed to make it super efficient? How does that then inform the decision, the research areas that we concentrate on? Lots of the work that is being done in particle physics research, for instance, is mostly boundary value problem. Even in things like protein folding problems, you give like boundary conditions, and that is what you have lots of PhD students who work on. And at the end of 4 or 5 years, they tell you that, well, I've looked between this condition and this condition. You're not going to find anything there. Next. So we should be able to make this much more efficient. So challenge, is this the next slide? No, please go back. Okay, the next one. No. Okay, cool. All right. So currently, our challenge definition process sometimes lack, and we benefit from a systematic evidence-based approach. Currently, participants' problem solving is driven by heuristic and social pressures rather than systematic evaluation, right? So what are the things that are in trend? What are the things everybody is talking about? But we understand now that this cannot be what drives like real innovation. If you go back, I don't know, maybe 2, 3 years ago, it used to be the metaverse, right? It was everywhere, and we thought that that was going to be the next breakthrough technology. In fact, it was so big, in fact, that Facebook renamed its parent company to be Meta, so they will be the name for the thing. But it did not turn out, right? And so we know better now than to let social pressures dictates the research focus. Another one is that the scientific community currently lacks robust methodologies for anticipating quantum breakthrough trajectories. The next slide, please. So how do we then go about building the quantum prediction engine? So what we look at is we're going to do data collection. We need this. We're going to do pattern analysis. And we're going to do some validation. Please, the next slide. All right, so for our database, we're using OpenAlex, which is sort of like an open source database for all the papers that have been published. So some of the things that we'll find in OpenAlex is that you find lots of papers, approximately 240 million papers. So it contains the papers, the books, the data set, everything is there. So it covers authors, institutions, journals, concepts, and more too, and offers structure, regularly updated data via its API. The next slide, please. All right, so we then did an analysis over this time. Remember that I said we need the data, we do an analysis over that, and we check for the validation on that. So after doing an analysis, we found this, which is not clear, but the core idea here is that there is dense interconnected concepts network that we can look at and be able to tell that, okay, these are the major research areas that are going to be maybe the breakthrough areas. Some research areas are matured field already. Some are emerging, and from this graph, we are able to tell that still a lot of work to be done anyways. So physics and qubits, for instance, are central, and there is clear structural pattern. Please, the next one. The next slide, please. All right, go ahead. So there's these two, and for this one, I'm not going to go into the details, but the important thing here is that we look at this heat map, and we're able to see that 49% of top-tier concepts are stable. We see that 51% of it is in decline. There's some sort of mobility, but I won't go. This is not exactly important. What is important to this is that we can see that the rise and the fall fairly predictably. Please, the next slide. All right, which is essentially whatever it is that I said on the last slide is still the same thing. That we see from here. This is not quite clear. I would have tried to explain some things. Please, the next slide. So beyond quantum computing now, we understand that this particular method is field agnostic, so it's not just limited to quantum computing, right? We could apply it to biotechnology. Through just a query, you just impute the field you're interested in running a query for, and it tells you all of these things. We could use it in artificial intelligence in identifying breakthrough algorithms. We use it in climate technology to forecast solution priorities. Please, the next slide. All right, so potential use cases. So this is sort of like, I don't know, you are doing Hackathon, so this is me giving, I don't even know what this is called again. So side trend dashboard, this is something that can be built. So real-time research evolution tracker. Technically, I thought I would be presenting this at the end of the thing. So, but anyways, so you could also build something like Research GPT, which would be AI advisor for field selection. And you could build a breakthrough bot, for instance, which would be maybe a Slack or Discord bot for trend alerts that, okay, this is an emerging trend. You should absolutely work on this. Please, the next slide. So what we now know, if we're going to build the future, we know, for instance, that quantum research evolution is now statistically predictable. We understand that predictive relationship patterns exist across all quantum computing domains. We have a data infrastructure that we can actually use, and that there's a massive but uncertain quantum market, like $850 billion by 2040 across sharply different competing technologies. And that with what we are building, you don't have to, we understand that most of science is based on trial and error, and that if you can make trial super efficient, then you can reduce the rate of errors in this research. Please, the next slide. So your quantum hackathon project could help a team avoid the dead, so we could help a team avoid the dead-end quantum algorithm approach. We could help thousands of hackathon participants choose winning quantum projects. Also, we could help organizers create relevant, forward-looking problems. The next slide. Thank you. All right.
Shall we have the next panel here quickly? All the panelists, please come. Please come up quickly.
Good morning, ladies and gentlemen, and a warm welcome to you, to first of all to Ghana and to the AIMS QTEdu event. So my name is Chantel, and I'll be moderating this panel discussion on the just ended NYUAD Quantum Hackathon. I have with me some wonderful panelists who were participants and mentors of the hackathon, and will be sharing some experiences that we had during the hackathon. So we'll start off by having a brief introduction of everyone, just who you are and what your role was in the hackathon. Let's start with.
Okay. Hello everybody, I am Alex from Cameroon and I do research at AIMS in Rwanda. So I attended the NYUD Hackathon this year, and I was playing the role of a student animator at the same time.
Hello everyone, I'm Priscilla. I just graduated AIMS Ghana, and I attended the just ended NYUAD Hackathon as a student.
Hello everyone, my name is Ola. I'm from Benin, and I'm a PhD student in quantum computing at AIMS Ghana. I attended the NYUAD Hackathon as a student animator. Thank you.
Hello everyone, my name is Fred, and I am a PhD student at the University of Ghana. And I participated in the hackathon last year as a student and a mentor at the same time.
Good morning, everyone. My name is Leila, and I'm a postdoc researcher at AIMS Research and Innovation Center in Rwanda. I participated in the Abu Dhabi Hackathon as a mentor.
Thank you for your introductions. So we'll get straight into the questions. Let me start with you, Alex. Can you share with us what your most memorable moment from the past hackathon was?
Yeah, thank you, Chantal, for the question. Yeah, I can definitely share it with you. So, my most memorable moment was like when we were just a couple of hours from the presentation, and then my team and I were actually struggling to run the code because it wasn't working due to the multiple errors. And then we were lucky enough that you had some great mentors, the other mentors, even though I was a mentor, but I was a student at the same time. So the mentors were actually kind of motivating us, and they were here and there, and like we were running out of coffee because we were stressed out completely. But finally, we were actually able to come up with a solution because we actually had to go to ask to other groups. And I actually advise the students not to only focus on their teams, but they can actually go outside and even meet the judges, because I believe that they have experiences, and to ask them some questions like, yeah, I think that was the most memorable moment. Thank you.
Thank you for that. Leila, could you also tell us what your most memorable moment was?
Okay, thank you, Chantal. Actually, it's the same as Alex. The most memorable moment during that hackathon for me was related to a challenge that the team I was working with faced. Actually, the team started by working on a big and exciting idea. But when they tried to make it work, the results didn't come out as expected. So then everyone got somehow confused. And you know, the time is very short during the hackathon, only 3 days. And this happened during the second day. So he didn't have enough time to fix the things. And they spent a lot of time to fix it, but it didn't work. So then the team decided to choose another direction, according to some feedbacks received from the judges during the hackathon. That was very helpful. And it was a hard decision to change the direction of the idea. But finally it worked and the things started making more sense. So at that moment, it really was very special, and it showed how important it is to stay always flexible and to listen to others, and also to move forward, even when the things don't go in as planned. You see.
Thank you very much. That's very insightful. Let's move on to Fred. Can you tell us about a very challenging technical issue that you faced in your group?
Okay, so in my group, we had done all the mathematics and all the calculations, and we were expecting that our code would run without issues. And about 2 hours to the final presentation, we had no meaningful results. And I remember we had other team members coming in to help us. And the issue was just that the browser we were using, it had some security settings that was preventing the code from running. So it was one other team member, so from another team, he came and he saw a little pop-up up there. And then he prompted us to check it. And fortunately, when we checked it and allowed the permission, our code finally ran. That is 2 hours to the presentation. Yeah.
Wow, that's very interesting. Okay, how about you, Priscilla? Was there any technical challenge that you guys faced?
Well, like as they all said, it was more about the code. So I think the nights before the day we had to pitch, we had also faced challenges with the code not running. But luckily, after they didn't sleep, so they awake all night trying to solve the problem, but eventually we were able to solve it and be able to present for our pitch.
Olan, what advice would you give to participants and mentors of this hackathon based on what you experienced at the NYUAD?
Okay, thank you. So, as advice, I would like to tell the participant that aside from winning a prize, it's also important to enjoy, because we are together for just a small amount of time, so it's very good to network and communicate.
Let's go back to Alex. How did the hackathon experience influence your perspective on quantum computing and your future plans?
Before going to the hackathon, I actually consider I had some experience when it came to quantum. But there's a difference between knowing something and maybe knowing how to teach it to other people, right? And I was in a team with people that were actually really new to that. But they have some other skills like in web development and other stuff, and even artificial intelligence and machine learning, but not really on quantum computing. So I actually had to go down to the bare knowledge and then start to teach them like from the ABC so that they can actually get some understanding before starting to work on the projects. Yeah.
How about you, Priscilla?
Okay, so before the hackathon, I think my experience with quantum was probably the lectures by Philip. So that was like the most experience I had at that time. And it was a bit theoretical, so the hackathon just gave me an opportunity to see how like I can apply it to solve actual problems in the world, and that was eye-opening and kind of a revelation, and it's also inspired me to try to find a way to also do my research in quantum computing. Yeah.
So it has impacted your future plans as well?
Oh yes, definitely.
Okay. Well, thank you very much for sharing your experiences with us, and I wish us all a wonderful event.
I want to change the schedule a little bit. So we go for break now, since we've been sitting for too long, and interact. Back in 15 minutes. And so we will start with your talk from Q-Braid before the main lecture after the break. So let's have some coffee and tea.
knew I was underwater.
Hello. Please, let's get seated.
Hello everyone. Okay, let's start. So I am Muhaymin. I'm from Algeria. I'm part of CQTech and I'm here representing Q-Braid today. I will be presenting the Q-Braid platform and the company and sharing with you the access code for the hackathon participants. So I would like first to thank the AIMS Ghana organizers and the Open Quantum Institute for organizing this amazing opportunity for African students. I wish everyone luck and please be stressed and do good and enjoy this, enjoy every step, enjoy every step of this. So let us start. So Q-Braid and what is Q-Braid? So you know how the quantum computing field is extremely interdisciplinary and it requires the efforts of physicists, computer scientists, and every other specialty to make it work and to bring quantum advantage like Philip showed us earlier. Q-Braid takes this as its core mission, where it tries to assist and facilitate the interdisciplinarity in quantum computing as much as possible. And we do that with four main steps. Can you change? So we have 4 steps in our process. There is the initial step, which is the Q-Braid Q-Book. It's an educational materials prepared by crew Q-Braid with demos and explanations and references designed to introduce people to quantum computing and all the fields and help them get started without extra in-depth information. The second part is the Q-Braid Lab. It's a Jupyter Lab IDE online that's available for you online, where you can code on it, launch it, code on it. You have more than 25 programming SDKs, quantum SDKs. You will have all the environments managed, the dependencies. Now you don't need to worry about installing Qiskit and installing this and that. You can just launch Q-Braid Lab, pick an environment, and get started on coding directly. I will show you later, it takes 5 clicks to get started on quantum here. The other very important part in Q-Braid is the Q-Braid SDK. It's a package developed by Q-Braid that allows you to interact with all quantum computers without actually knowing all the SDKs. It is a very, this problem appeared back in 2019 when with the emergence of quantum computing, we had a lot of companies and each one developing its own quantum technology and each developing their own SDK to run quantum circuits on their backends. And what you needed to do if you're gonna run on IBM, you're gonna need to learn to code in Qiskit, code the circuits in Qiskit and execute. Then you're gonna move to want to run on another. For example, if you run on Google Quantum Chips, you're gonna need to learn Circ and develop circuits in Circ, which is too much and does not support the interdisciplinarity of things. So what Q-Braid did is they created an SDK that transpiles between languages. It's SDK to SDK transpile. So what you do is just like you learn Qiskit. Okay, you code in Qiskit, you do your circuit in Qiskit, and then you run on IBM stuff. If you want to test it with test it against in Quantinuum, you do not go and recode anything. You just use the Q-Braid SDK. You transpile a Qiskit circuit directly into Quantinuum, and you run it in just a few lines of code with no knowledge of PyTicket, for example. So when we benchmarked back in 2023, we benchmarked the Q-Braid SDK, and it was the best SDK performing in SDK to SDK transpilation. It was the most general one. The fourth part, which is an infrastructure thing, it's the Q-Braid runtime, where it's an optimized on the cloud running, where you can compute when you combine classical algorithms with quantum and run everything on the cloud without delays with your internet or anything. This is made available through Q-Braid. Accessing quantum hardware in Q-Braid is even easier than I was saying. There is 3 ways you can access. You can access directly on the website with GUI. So if you have no experience at all, you can just go to the website and run circuits from there without coding, without Python, without anything. But if you are a seasoned computer scientist and GUI bothers you, you can access it through the command line, and it suits everyone. And if you are like me, a physicist with some Python experience but not that much to enjoy CLI, you can access based on SDK, and it makes the quantum computing job extremely easy and fast for you, so you don't have to worry about anything. Also, besides the platform, Q-Braid is a top startup in quantum computing research. Move to. It has one of the 8 teams that won the phase 2 grant of Quantum for Bio Challenge. This team is led by Kenneth Heritier, the scientific advisor of Q-Braid. They are working on biology-related protein folding problems with quantum computing. Q-Braid supports a lot of research in quantum computing and workforce development. Can you change the slide? So we do a lot of research in quantum computing. We support, there is internships for students, there are jobs, there is also through partnerships like this one and other, we support regional workforce development, and the whole mission is to make quantum computing accessible for everyone from all over the world and from all kinds of backgrounds. So now, I will speak about introduce the Q-Braid quantum platform. It's your one-stop quantum computing platform. Go ahead, these are all slides that are animated technically. Move. Yeah, it's the platform. Okay, just before this one, I said to move fast because they are animations and they were flattened in the PDF. Okay, before. Yes, stop here. The platform has 3 axes, and we'll see them. It has the comprehensive Jupyter Lab browser, as I said. It is the most used Jupyter Lab browser IDE in the world. It has, you enter, you access, you open an account, and move to the next slide. It's easy, just 5 clicks. Open any GitHub repo managed by Q-Braid. You find the button that is launch on Q-Braid. You click on it. Within 5 clicks, you open your account, you pick an environment, and you start coding. And then if you want to change and install extra packages or SDKs to use, you can directly You have a pop-up list as shown in the demo by Ricky. You can pick whatever SDK you want to install and install it directly and continue working without extra managing of environments that you do locally. And this is really helpful. For example, I am a chemist myself. I work on quantum chemistry, and there are packages that don't work on Windows, and they have problem of going and installing Linux connectivity, which noise suits your algorithm better. This is the faster way to do it. There is unless you want to code everything from scratch yourself in different SDKs, which is on its own a lot of work. And if you are, okay, can you please move on beyond this? Yes. Okay, stop here. This is the SDK. You need the API key that you get from the website, from your account when you open one. It's free, and you can use different ways to bridge towards. You can, for example, here we have circuits. We create a you create a no. Just go back quickly. You create a circuit and then you want, for example, you are translating them to bracket to run them on Amazon. You just use the transpile imported from Q-Braid transpiler, and you can run it directly without knowing bracket at all. So move past it. As Q-Braid runtime is optimized, the cloud is optimized. There is GPUs, there is Intel CPUs. It's connected to other quantum computing technologies. So it's optimized for you to run your quantum code at the most optimal way possible. Direct connections, fast internet, GPUs to accelerate the classical part in quantum in hybrid algorithms, so you do not waste any time in it. But if you are a seasoned if you are a seasoned coder and you would like to code on your own PC and not on the cloud, then we have an extension that allows you to work with Q-Braid still. It's Quantum Console, Q-Braid Quantum Console on VS Code. You can install it, insert your API key, and you will have what you need to use Q-Braid. You will have a live connection for the quantum devices available, quantum hardware available. All you need to run your Q-Braid codes, you have credits, you have everything, without going to the cloud. If you are working locally, there is still the console to help you. So it literally suits everyone that wants to work on quantum computing with no problems at all. So this is the single extension for everything. It's the quantum console, and in the demo, by Ricky, he showed you how to use it, and the link for the recording of the demo that happened Friday will be shared with the students in case you need it, and I will be here, I am here personally to provide you support with anything that you need from the Q-Braid side. Device availability. We have on Q-Braid now, we have the Q-era devices. They are quantum neutral atoms, quantum computers. We have Rigetti, another superconducting technology, IQM, IonQ with trapped ions, and there is also the IBM quantum free instances. You will have credits. I will share with you the access code. You will have credits to run your codes on this in this hackathon, but I stress this: use simulators first. Use local simulators, use Q-Braid free simulators. Do not get really excited about running stuff on quantum computers that you use your credits when you are learning. Quantum computers are really expensive to access, and they are not, and there is a lot of queue time and a lot of other problems. So please, when you're developing, just use simulators. When you are sure and you are done and you want to get the real results and you are sure your algorithm works with no bugs, that's when you use quantum computers. This is not just for this hackathon. This is how researchers do it all over the world. We never use quantum computers directly. We do simulations, we test, until we are sure that our stuff works, and we want to get, with the only thing remaining is the quantum computer results. We run on quantum hardware. So please be mindful of that, so that you do not exhaust your credits in the first day, and then when you have exciting results to get, you will not have credits. So this is the access code. It's Global Hackathon 2025. You can take a picture of it. I will give it to you. If anyone misses it, I will share it with you. It should be active now, but as I said, I am here to provide support, and please, anyone can approach me about it anytime. And there should be hardware available upon review. For the projects, once they are done, if there is an interesting enough approach that you need extra credits to run quantum computing simulations. It will be reviewed by the Q-Braid board, and we might give you extra credits to run your algorithms beyond this quantum hackathon. That is, if the approach is interesting to work and pursue, we will provide access to hardware. And the demo, as I said, the demo is supposed, but we don't have time for it. The demo will be, the link will be shared, and it had already happened Friday with Ricky, but I will share a recording with you, and I will be here. This is you can scan this code to have all the Q-Braid access, all the Q-Braid codes, the Q-Braid links, sorry. All the Q-Braid links, you will find the platform, you will find the demo GitHub repos, and as I showed you, you will find always a launch on Q-Braid icon where you can start running stuff on Q-Braid Quantum Lab. And thank you very much.
Okay, thank you so much. We now have the keynote talk. I have already introduced Ian, the provost for Imperial College, and he is a quantum expert, and he will talk to us about light in the quantum future. Thank you.
Thank you, Prince. Well, I'm honored to be here talking to you and to be invited to this fantastic quantum hackathon. So congratulations to AIMS and to Prince for organizing this. I think it's a really exciting thing to be doing, and I look forward to seeing the outcomes of all your efforts later on. So I will talk over the next 40 minutes or so about particular research in quantum simulation and quantum processing, related very much to quantum computing, but I'll talk in very particular terms about light as a medium for doing that. And I'll explain why I think that's very much related to things like sustainable development goals as I go on. As Prince noted, I'm currently at Imperial and have been fortunate to have support for this research from a number of agencies over the past few years. And just to note that I'm also a co-founder of Orca Computing, which is a company that builds quantum machines. Since I'll use a bit of their material later on, just so that you note to register any potential conflict of interest. Oops, does this, there, great. Now, I will talk about a number of areas, so I want to recognize and acknowledge all of the people who've contributed to the materials that I'll talk about, a number of people who are currently in the group at Imperial, as well as those who have moved on to other things, including the team at Orca and Southampton. We've collaborated a lot with former Sewu Nam's group at NIST, and currently with Gerard Milburn in Sussex, and colleagues Myung-Shik Kim, Raj Patel, and Steve Kolthammer at Imperial. Okay. And then just to note here a sad event of the past few months, which is the passing of Joe Eberly, who's the second guy on the left from the left here, one of the real pioneers of quantum optics and a major contributor to the foundations of the work that I will talk about. So that's a loss for the community, and there will be some celebrations of his life over the next few months, especially from work in publications in Optica. Okay, let's move on. So light. Why should you care about light? Well, you've heard earlier from Philip about other platforms, in particular ultra-cold atoms. You've heard from our previous speaker, or you saw an illustration of superconducting quantum circuits held at very cold temperatures. And you have perhaps also heard the other major platform of trapped ions, so cooled, optically cooled, and held in a vacuum. All of those systems share a very important feature, is you have to get them down to very cold temperatures, at least in the millikelvin regime, before they all work. With light, you don't have to do that. It is a medium which shows quantum features and can manipulate quantum features in ambient conditions. And that's extremely important if you want to build machines that are compact and fit in directly to current architectures, especially in regions where you don't have major infrastructure. You'll know, of course, that light already is the main medium for long-distance telecommunications, and the global optical fiber network is the backbone of the internet. And that's the reason for that is the extraordinarily high information capacity that light has. And moreover, not just that, but the fact that optical channels do not interfere with one another because of the way the information can be coded in an optical system. That's a great thing for communications. It turns out that it makes things like computation a little more difficult. So I'll talk a bit about how people approach that, because as with all platforms, there are very fierce technological challenges to overcome if you actually want to build a fully scalable, fault-tolerant quantum computer out of light. Just to note at the bottom, a recent article from a couple of years ago, which is a sort of high-level view of how light allows you to build quantum computers and quantum simulators, in case you're interested in more detail. Okay, let's go on to the next slide. So you've also heard a bit from Philip about graphs, and I'm going to talk quite a bit about them. So I want to give a little bit of motivation for that, which is that a physical network has a great deal of inherent similarity to a graph, because these are the sorts of things that you already use for distributed classical computing, for distributed sensing, and of course for communications. They have an important element in scaling as well, because they only require two kinds of elements. One is a node, which generally has some processing or memory capability, and then a channel which connects those nodes, which has the transmission capability. And the great thing is that that means that they are they're manufactured out of a very small number of components, and they are very highly reconfigurable. So if you get errors or imperfections, you can work with them. Now, the reason that optical networks work so well for classical communications is that you also have an important element, the optical amplifier, which means that as your signal gradually degrades, you can amplify it. The challenge with a quantum network is that you cannot use amplifiers, because they degrade the quantum correlations that are at the heart of what you need to do computational simulation very, very quickly. So you might say, well, without amplifiers, how can I possibly scale? And the answer is, if you have a quantum memory, then you can overcome that essentially by a repeat until success method. And that turns out to be a polynomially scalable way of approaching these things. So, quantum networks, which have this very strong similarity to graphs, are a basis for doing all these kinds of things. Here's two examples, both quite old now, about 25 years old, but still, and they're certainly not the modern versions, but I think they illustrate why people have pursued this. One is a communications network, where the idea is that you'd like to distribute entanglement from across a long distance. So that illustration there, it shows Imperial right at the center, of course, connecting to everywhere. That's the way we like to think about it. But if you want to share entanglement, you know, with Marcelo in Brazil, or Karen in Argentina, or elsewhere, then what you have to do is transmit a quantum particle to establish that over some distance. And of course, the longer you go, the more likely you are to lose that particle. And that scales exponentially with distance. So the idea, originally Hans Briegel, but I've shown the DLCZ protocol here, is that what you do is divide that up into small elements. You create entanglement over those small elements probabilistically, and then when that succeeds, you hold it in a quantum memory. And that's the little device in the box on the left-hand side. Then when all of those memories are primed, you connect them together, and that connection allows you to do entanglement swapping over the entire link. So that, they showed, was a scalable architecture just using linear optics and memories. On the right-hand side is the very famous KLM architecture, showing that with light and detectors alone and linear circuits, you can build a fully scalable quantum computer. And you see again the sort of network architecture where there's a lot of interconnections between different nodes, and then here you put 3 photons in on the right-hand side, on the left-hand side, by conditioning measurements at those detectors D1 and D2 on the right. You can effect a nonlinear sign shift gate on the upper elements of that circuit. Now, that's not, again, the modern way it's done. I'll give you an illustration of how people now think about it, but it does show you the basis by which these very simple interactions can lead to a scalable quantum computer or communications network. Now, let me turn first to how you build a quantum simulator out of light. Let's see, will that go on? Thank you. And here is the very, very simple idea. So let's just take the diagram here. You put some sort of quantum light in on the left-hand side. That could be, for example, individual quantum particles of light, single photons, or it could be some other more complicated quantum light source. On the right-hand side, you have a set of detectors. And those detectors need to be very, very sensitive because they need to be able to count individual photons. And of course, they have very, very tiny energies of about sort of 10 to the minus 19 joules. In between, you have an elastic scattering network. That simply may be a bunch of scatterers where the light bounces off, or it might be a bunch of beam splitters where two light beams can interact with one another. Importantly, it doesn't do anything other than that, so there's no active or nonlinear interaction between the two. What's remarkable about that system is if you ask, given n photons at the input and an m by m scatterer, tell me what the photon distribution is at the output. You'd think in such a simple problem that would be a very simple thing to calculate, but it turns out to be computationally very difficult to calculate the output of that photon, that network, the photon number distribution. Moreover, it's not just hard to calculate that distribution, it's hard to even sample from it. So you have an inherently complex problem in a very simple system. And that idea was first expounded by Scott Aronson and Alex Arkhipov in about 2011, 15 years ago, where they came up with that concept of a feasible quantum advantage using simply a quantum interferometer and the particle statistics of bosons. Hence it's called boson sampling. Okay. Let me just illustrate to you the very simple mathematics of why that is the case. So I've illustrated here a very simple linear scatterer. There's two beams going in at the input, 2 beams coming out at the output, and those beams meet at a beam splitter. What's that? Essentially just a piece of glass. You know that if you look at a piece of glass, you see 2 things. You can look through it to what's ever on the other side, and you'll often see a bit of your own reflection in it. Well, that's all that piece of thing is here. Of course, more specialist, built to give you an arbitrary scattering ratio, et cetera, but that's the basic physics of it. That's simple. And you can describe the operation about how the output modes, gamma, delta, connect to the input mode amplitudes, alpha, beta, by a simple transfer matrix here, 4 elements, A, B, C, D. Now, because that's a linear system, what that means is the particle number, the number of photons, has to be preserved. If I put 2 photons in, I get 2 out. If I put 5 in, I get 5 out. That means that T has to be a unitary matrix, and therefore its determinant is 1. So that means AD minus CB should be equal to 1. Okay. Now, here's what's interesting about using that in the quantum domain. And this is something that Len Mandel discovered in 1987. If you put exactly 1 photon in each of the input ports, alpha and beta, then ask what's the probability of detecting exactly 1 photon at each output port, C and D, it turns out it's equal to the square of the permanent of that transfer matrix, AD plus CB. And that's quite remarkable, because if you think of those photons as simply classical particles, you'd say, well, it's very simple, it just happens half the time. Half of those possible outcomes will be this. But that's not the case here, because these are quantum particles, and therefore there's quantum interference. Now, the key thing is, well, first of all, very interesting physics. That probability can be equal to 0 for a 50-50 beam splitter. So if I'm just thinking about these as classical particles, I say must happen half the time, quantum mechanics says no, doesn't happen at all. And that's a remarkable feature. But the mathematical statement that it's the square of the permanent of that transfer matrix is important because, as Valiant showed in 1977, there is no efficient algorithm for estimating the permanence of a matrix. And that is the origin of the computational complexity of the optical simulator. Okay. So with that in hand, I'll jump now to current ways of using this device as a simulator. So same thing as before, now formally structured. Quantum light at the input on the left-hand side, a linear matrix described by a transfer function T, and detectors on the right-hand side. Now, I've changed the quantum light states to something called squeeze states. I won't go into what those are, but if you want to talk about them at the end, we can do so. And importantly, that bottom line, coherent states, that's like a classical input source. So I've got some classical light that goes in there as well as the quantum light. And I want to use that to see if I can scale up the system. On the right-hand side, I've shown detectors that now are able to resolve photon numbers. So not just counting 1 or 0, but they can count 1, 2, 3, 4, 5 photons. And that's also a fairly sophisticated piece of hardware, and that's the group at NIST are real leaders in that area. So now if you calculate what's the joint probability distribution of photon numbers at that output, and that's sort of illustrated in this graph here, sort of this random distribution, it turns out that it's related to the Hafnian, that's a function which is like a double permanent, if you like, of the transfer function of the system plus the squeezing that you go into. I'm not going to talk in any detail about the detailed mathematics of that, but suffice to say, just as I illustrated why calculating the permanent is a hard problem, calculating the Hafnian is equally hard. And that was a result from Chris Hamilton and Igor Yeks about 7 years ago. And that idea of that has been taken forward by Janwei Pan's group in USTC, in which they showed back in 2020 a system which demonstrated quantum computational advantage using exactly that system. And the diagram in the lower left shows you the components that I've said, the input light, multiple squeezers coming in from the right-hand side, an interferometer, which is a glass block in the center, not reconfigurable, and then the outputs going to multiple detectors on the left-hand side. You see the size of that system, here is an optical bench, so roughly 2 meters by, or 1.5 meters by 2 or 3 meters, and you can see the complexity of that setup there. So very, very simple system, not a universal machine by any means, just running this specialist boson sampling algorithm and showing that they were able to build something which would require a great deal more time to simulate on a supercomputer. They have been followed by other groups have done similar things now, of course, but the challenge now is to identify the applications for which this is useful and to build a reconfigurable system. So this is just the system that we use in our lab at Imperial, which is by no means in the quantum advantage regime, but is intended as a test bed to check out certain algorithms. We use a 6-source squeezer shown on the left-hand side, a 10 by 10 mode silicon nitride photonic integrated circuit, which is fully reconfigurable, that's shown in the middle. And then we have transition edge superconductor detectors, which you can see here show resolution. This is the voltage versus time. You can sort of see there the photon numbers, different photon numbers being tagged in the system. Just to show an example of how one uses modern machine learning techniques to improve that system, here again is the output of these transition edge detectors. You can see the time scale here is microseconds, so roughly 5 or 6 microseconds to run to get one signal out of the detector. So here's a sequence of the output from these detectors running at around 100 kilohertz. And you can see that the fact that these have a finite response means it limits how rapidly you can acquire data. So what we wanted to do was to figure out whether we could improve the rate of data acquisition using machine learning. And the problem is very straightforward. As you go from 100 kilohertz to 500 kilohertz, you see that the traces start to blur into one another. And when you get up to 800 kilohertz, so nearly a megahertz, you think that's going to be quite hard to tell how many photons are in each pulse here. And indeed, if you look at the distributions, you can see down there that it looks so totally blurred that you'd think on the right-hand side you wouldn't be able to get any information at all. But Zhenghao Li, one of our PhD students, together with Raj Patel, showed how to apply a sort of forest classifier machine learning algorithm to really be able to discriminate between these photon number distributions with high fidelity. So this graph here shows the total variational distance from the data to the what we think is the ground truth at different repetition rates, and you can see that you get a considerable enhancement. So there's just a simple example of how the technology improves. So what are the opportunities for photonics in this sort of application? What I've shown you there, I hope, is that quantum machines can generate some probability distributions much faster than classical machines. So how do you harness those? Well, here's 2 examples. One is random circuit sampling, where you entangle a large number of qubits using some circuit, and you measure the resulting state, and that distribution is known to be hard. The distribution's close to uniform, and therefore it's often used just mainly for proofs of feasibility. But in boson sampling, you can get similar scales of tens of photons by the sort of boson sampling architecture I showed you. And again, as I illustrated there, that the distributions are highly non-uniform. And the fact that you've got a structured distribution allows you certain applications in machine learning and optimization, because your search space already encodes some of the features of the problem in a helpful way. So here are some of the advantages we think of when we think of photonic implementations. You can use fairly shallow circuits, and importantly, because of that network architecture, you can use non-local circuits as well, which is much harder if you're using an integrated computational platform. You get distributions with with strong correlations at all orders, as opposed to things that are hard to distribute from uniform distributions. It's not restricted to binary distributions, of course. I already showed you that you can get multiple levels out of this. And the distributions are fundamentally different than those available in qubit-based NISQ machines. So those are all features that you can really utilize and particularly explore in distribution sampling. So here's some roles of tasks that you might want to apply this to. Optimization, machine learning, and averaging. So that might be useful, for example, in Monte Carlo. In machine learning, generative machine learning algorithms are indeed sampling algorithms that look at how to extract something from a desirable data distribution. And optimization are essentially work by something like simulating annealing by sampling from the space of solutions in a possible solutions in a particularly smart way. So that's where we think the ability to sample from distributions can be useful. Let me illustrate that now in a particular way, and what I will do here, I won't go into the details of the graph theory. You've seen earlier that there are good analogs here, but I want to use this as an illustration for some of the challenges of scaling up. So a famous result from Arizola and Bromley from 8 years ago or so showed that it's straightforward to map a Gaussian optical system, that's essentially the system I showed you earlier, onto a graph by encoding the adjacency matrix in the transfer function and squeezed mode input. So in that case, very simply, the number of modes sets the number of vertices of the graph, and the degree of squeezing and the ways in which those modes are coupled are related to the edge weights. And now, if you look for the density of particular subgraphs within that graph, that's fully connected subgraphs, that's proportional to the Hafnian of the graph adjacency matrix. And therefore, sampling is intrinsically more efficient way to identify these than a classical search, for the reason that I showed you earlier. Evaluating or estimating the Hafnian has no efficient classical algorithm. I won't talk about the diagram at the bottom, but just to show you how we tested that out in a small scale machine. This is a different kind of boson sampler now, because rather than encoding in the spatial modes of a photonic integrated circuit, it encodes in time bins. And of course that's, as you saw earlier, that's related to the rate at which you can sample from your detectors at the output. So just to illustrate that this setup here is essentially a squeezed light source that produces one squeezed beam here and one squeezed beam here. You send those into a beam splitter that builds them into these into a single mode squeezed beam here, that then is clocked at a certain rate depending on the repetition rate of your laser. And so that you take the first bin, and that's split into one which goes to your detectors and one that goes around the loop, which can then interfere with the second time bin coming in. And so you can do that across any number of steps that you like. And then you again sample the photon statistics at the output. And here we built something that was encoding a 10 vertex graph, and we wanted to find the 4 vertex completely connected subgraphs within that. And what the graph on the lower left shows you is an estimate of the density of those subgraphs versus the number of samples that we took. The horizontal dotted line is the ground truth for that graph. And what this shows you is that as you change the degree of squeezing, you can converge into that ground truth more rapidly than if you just run a classical stochastic algorithm, which is this purple line here. So this at a small scale illustrates the fact that you've got a more efficient way to do these graph sampling problems using GBS. How do you go beyond that? Well, here is a collaboration with the group in USTC, my colleague Shang Yu led. What this is now a more sophisticated version of that time bin machine I showed you. And the key sophistication is that this is now programmable, whereas the previous one I showed you was static. And what this allows you to do is to encode different sorts of problems in it. And this one is a version of the molecular docking problem, where what you're seeking to do is to identify the right location into which a particular molecule can dock. And that's very relevant to drug design and drug evaluation, because that's exactly what you seek to do, is to, with your target identified, you seek to find a molecule that will optimally fit with that target in order that you can produce, for example, a new vaccine. So that's the same problem, a graph search problem, to identify the maximum fully connected subsets of a large graph. Now, moving on now to how we use that in a machine learning setting. In a generative adversarial network, what you do is to take your empirical data distribution and use a discriminator to try and determine whether it's different than a randomly generated data set. And you train your discriminator by sampling from your observed data, from your test data set, and a set of random generated data. And after that training, you can have a learned distribution where your discriminator has a high probability of selecting the correct of classifying the input as a particular, for example, image based on data that you send to it. So how you train this discriminator, you can see, is critically dependent on the generator data, the generator random sequences that you use. And that is based on what the latent space is in your adversarial network. And so if you make that latent space trainable, you can generate an improvement in the operation of the discriminator. And it turns out, and this is work of my colleague William Clements at Orca, is that you can adjust that latent space by sampling from a Gaussian boson sampler that has been programmed with some of the features that you're looking for in the first place. And that turns out to give you some significant improvement in the performance of your discriminator. Now, an important point here. This is not an exponential improvement in machine learning. This is a small, an improvement in the overhead. But I think an important point to make here is that what this illustrates is that it's a quantum-enabled application enhancement. So it's nevertheless an importantly valuable enhancement to what you can do in a real-world application, even though it's not anywhere near an exponential advantage. Okay. So this is just an example of how we do that, using a commercial photonic quantum processor to build the latent space to provide that advantage in a discriminator. Here's just some outputs of that to two case studies. One is denoising, so taking an image of land use from a satellite and then getting rid of the clouds by denoising, and then finding something that very well closely approximates the ground truth for that test setup. Similarly, building a high-resolution RGB image, given that you've got the low-resolution one when you've properly trained your algorithm. So those are areas where you get a significant, 20 to 25% reduction in the classical compute resources that you need by having this quantum coprocessor. Let's go to the next one. So those are all small scale, and the obvious question is, how do you build that up to a quantum advantage regime in these hybrid applications where what you're doing is taking a random quantum sequence and using that to seed a classical algorithm. How do you build that up to a scale where you've got real quantum advantage? As I told you, the number of nodes that you can search in a graph, for instance, is proportional to the number of photons you put at the input. So the key is, let's increase the number of photons. And the challenge is that quantum photons are very expensive, whereas classical light all around us, very cheap. So can we use some classical light to boost the scale of these systems without losing the quantum advantage? And this was just an illustration that Guillaume Thakadath did for his thesis to try and see whether by adding to our system, see 2 modes of quantum light here and a single classical light beam there, where you can adjust the amplitude of this beam, and to see whether the distribution that you sample at the output can be efficiently emulated or distinguished from a quantum distribution as you crank up that classical light beam. Let's go to the next one. And this is the output. So up in the upper left are distributions compared with theory for 2 different classical light beam inputs. This is where there's only quantum light, and this is where there's 15% classical light. First of all, what this shows here on the right-hand side is the rate at which you see these n-fold events versus the amount of classical light that you put in. So the hypothesis, I said, is you can get much bigger systems if you put more classical light in. And you can see that you can get about 4 orders of magnitude improvement in the 5-fold coincidence rate by adding classical light. The question is, when you add that, can you distinguish that from just a classical light beam statistics? And the graph in the bottom here shows the distance of these distributions from an simulated distribution versus, again, the amount of classical light. And the key feature is that this is the classical light, here's the fully quantum one, and you can see even here, where you've got a mean photon number of 1.5 of classical light, that you can actually distinguish the classical and quantum distributions. So what that says is, yes, you can add quite a lot of classical light and still get something which has a quantum feature in it. Next slide. And now the question is that really complex? Eventually, this becomes sort of homeopathic. You have 99.9% classical light and 0.1% quantum. And you've got to think, well, that's got to be, there must be some approximate way to get that very, very precisely. And the answer is you can. This is work of Zhenghao Li in his PhD thesis. And this illustrates the following. So the graph, the sort of diagram at the top shows what happens as you increase the amount of classical light. And that's measured by the amount of classical light over the amount of quantum light, roughly speaking. On the far left-hand side is where you have no classical light. Well, I've already argued that and others have proven, that that's truly in a regime of quantum complexity. There is no efficient way to sample from the distributions there. This one is when there's all classical light, and as you might expect, there are then very efficient classical systems because there are just straightforward probability distributions that you can write down that emulate this one. So somewhere in the middle, there's a transition between it being a quantum machine and a classical machine. And the question is, where is it? Is it right over here, or is it right over here? And what the previous experiment shows is that actually it's probably a fair bit towards the right-hand side. And what Zhenghao showed in particular is that ratio, that hardness transition occurs when you have about 1/10 to 10 times the amount of classical light than you have quantum light. And that depends a bit on which algorithm you're using and how confident you want to be that this is truly complex. But even 10 times classical light compared with quantum light gives you a huge scale up in the system that you can have, and for most problems, pretty high confidence that this is still a quantum advantage system. And here's an example again for the molecular docking problem. This is now a simulation that Ewan Mayer did for his thesis. And what this shows is the success rate at identifying the maximum cliques in the graph versus the iteration step of the local search algorithm. So this is how many steps you need in your classical algorithm once it's been seeded by the quantum sampled output. And what he has shown is that when you have significant classical light in, that's this green curve here, you can get a significant estimation advantage over what you'd get with quantum light alone or with just a classical sampler on its own. Now, what happens to the complexity argument is that if you've got money, unlimited resource, and you use only quantum light, you will get the maximum complexity advantage. But if you dilute that a little, and that's what this graph here shows, this shows increasing amount of classical dilution, you can still get a significant quantum advantage by that means, even though it won't be as great as you might have had. That advantage won't be as great as you had if you had fully quantum light. So there is a way now to think about large-scale systems with high probability of quantum advantage, which can apply to these sort of real-world problems. And let me just sort of finish on this and the next couple of slides, which is so much for that sort of hybrid simulator system. What happens if you really do care about a large-scale fault-tolerant quantum computer? And this is the kind of structure that people are now thinking about. This is not the most modern structure, but it gives you an illustration. What you try to build is something called a cluster state, and what these each represent is, say, a photon where the connection between them is an entanglement. So you can see these are quite complex entangled structures. And that allows you to build a measurement-based quantum computer for which light is particularly well suited, as opposed to a straightforward gate-based one. And in a measurement-based one, what you do is prepare these universal states. You then make a set of measurements, and then the next measurements that you make, which is how you encode your algorithm, are conditioned on the outputs of the first ones. So that's why optics is well suited to this, because you can build these general states and then use the latency of the state preparation to continue to add on to them. The challenge is, as I said at the beginning, that light tends not to like to interact with other beams of light, and that's why it's brilliant for long-distance communications. But that's what makes it particularly challenging here. So I showed you the KLM scheme, whereby you use detectors to conditionally prepare entangled states. And with that conditionality, you have to try many, many times until you have gotten the right setup. And so the way you have to do this is sort of start here with small systems of 2-photon entanglement, and then you have to try many, many times until you get a success where those two are entangled together. And then you use that to build up something like these more complicated leaf structures and then you have to do that at yet another level here, and then you have to entangle 2 of these. So these you have many, many nodes on, because you've got to try many, many times, and the number of nodes you need is dependent on how probable your entangling operation is. So you can see that requires a huge number of photons and a huge number of modes and a huge number of detectors. Now this illustration from Simon Benjamin is a decade old, but at that time the numbers were sort of 1 million to 1 billion elements per data qubit, per logical qubit. Nevertheless, the engineering challenges are things that you can tackle, and several companies, PsiQuantum, Xanadu, our own Orca Computing, have been pursuing this approach. So just to illustrate that entangling operation, how does it work? Here's the basic physics of it. So start on the right-hand side. I've got 2 modes, and I'd like to make the output an entangled state. So entangled state here is 1, 0 plus 0, 1, or 1, 0 minus 0, 1, where 1 represents the presence of a photon and 0 represents the absence of a photon. So if you like, your logical qubit is encoded in these rails here. Now, I put 2 photons in, 1 in each mode, deterministically. And I then use these 2 beam splitters. And now, this photon has some probability of going here, so does this one. And I mix that here, and I do that, by doing that, I erase the information about where this detection event can come from. So I look for one of these detectors firing. This detector setup has received 1 photon, but now I don't know whether it came from here or here. And that means the complementarity is that leaves an ambiguity out here. So I have an entangled state here, which is complementary to this entangled state there. When one of these detectors fires, it collapses that and leaves me with an entangled state there. So that's the basic principle on which you generate entanglement out of single photons. And then these diagrams here just show you how you build up more complex states from that. And this diagram here, you have 6 photons in 6 modes. You look for a detection pattern out of those 6 detectors, 3 fire, leaving you with a 3n GHZ state over here. And you can scale that up to whatever state you like, with decreasing probability of success in any shot, but that allows you to build a base set of resource states, and I'm not going to illustrate this in any detail, but with those sorts of bell-type measurements and these sort of leaf structures, you can build up your complex 3D computational state. And that's your basic resource state generator there. Lots of modules which include squeezed light sources, integrated circuits, switches, and detectors. And what's the loss tolerance you need? Well, this graph here shows the best code I'm aware of, which is Brendan Pankovich's, the single photon loss rate going from, I think that's 2% to 12% at the top, and the number of photons that you need in each resource state, so how many photons you have to have at the output of that thing to tolerate that loss. And you can see that if you, in his code, if you want to tolerate 12% loss in your system, then you have to have 100 photons per basis state. And that's a huge overhead. But if you've got down to 2% loss, then you need about 10 photons per basis state, so 10 times less. So the challenge in all of these systems at the moment is how do you get your loss budget to accommodate the number of processing steps you need per photon. And that's not easy. You need down to 0.01 dB per element, essentially. So that's the challenge. And I think probably that's, I'll finish there. I won't talk about processing networks using memories, but I'm happy to answer questions or talk about that with you later on. But I think I'll finish there now. So maybe we could just go to the last slide, please, for that. A few more through there. Boom, boom, boom. There we go. That was on. Previous one from this. There we go. Fantastic. So really, I've talked here about quantum simulation with light, that Gaussian boson sampling can be scaled for useful applications using classical ancilla, and there is a regime of hardness even when you have a good deal of classical light in there. And that this allows you to use these quantum statistical distributions as an input to classical algorithms that allow you improvement in classical machine learning tasks. And then I won't talk about the rest, so I'll finish there, and thank you very much for your time.
Thank you very much. We have time for a few questions. Okay.
Just a very simple question. Can you use machine learning techniques to improve your bosonic sampling? So on the contrary to what you were doing, because you said that the quantum sampling can help machine learning, but on the other way around, if you can use machine learning to improve the sampling.
Yeah. Yes, that's right. So I gave an illustration of how we used machine learning to increase the sampling rate, the rate at which we could run the experiments, by improving the detector readout. So that was an optimization of the signal processing of the output that allowed us to run the sampling algorithm faster. So once that just allows us to sample more rapidly from the quantum distribution. And then we use that as a seed for these GAN algorithms or graph search algorithms. So yeah, I was trying to illustrate, sorry if I didn't do it well, that machine learning helps you both in the experiment design and operation, as well as quantum then helping these machine learning algorithms in other settings.
Okay. Okay, 2 more questions.
Yeah, thank you. My question is related to her. So I wanted to find out if there is any relationship between machine learning and quantum computing. But you've explained that you use machine learning to help to do your things in quantum computing, and that's fine. Thank you very much.
Thank you.
Thank you very much for your presentation. I want to know how this approach of photonic is a promising candidate for quantum computing compared to other approach like topology and quantum information and also on.
Yeah. Okay, so your question is how does photonics compare with other platforms? And you also mentioned the topological computer, and I didn't mention that, well, partly a deliberate omission. So on the other platforms that I mentioned, so there's cold neutral atoms, there's trapped ions, and there's and the superconducting machines. Superconducting and trapped ions have generally focused on gate-based architectures, and of course that means you've got to build very high fidelity gates, which they have largely succeeded in doing. But then you've got other sorts of challenges. So in a superconductor, in superconductor you certainly have a circuit which is fixed adjacent qubits. So if you want to do connecting, get qubits 1 and 5, you've got to go through a chain or a network. That means your fidelity has to be particularly high. You've also got the challenge in the superconducting machine that to get your control lines in and out on a circuit that's big enough, you've got a real bottleneck. So those are the problems that I think people like Google and IBM are currently trying to solve. The neutral atom machines are also generally analog like the photonic ones, but the way that they are most useful at the moment has been to directly simulate particular Hamiltonians. So encoding their interactions directly into how you manipulate your atomic arrays. They can currently get up to about 10,000 atoms, I think. How you get up to the 100,000, I think, is still an open question. The key piece that I would say photonics has an advantage for is you can run this all at room temperatures, except, as I illustrated here, your detectors need to be cold. But that's the only element that you need to do. So what that means is you can build these small quantum advantage machines, non-universal machines, into an optical rack with a small cryodetector assembly in there. That means you can put them directly into a data center, and you have immediately a quantum element to your hybrid computing machine. So I think there's some real practical advantages to using photonics, although when we get to the full fault-tolerant machine, I think the question still remains open.
Okay, maybe before you sit down, my question is related to that. So we were in the workshop in Durban a week ago. A lot of people in quantum across Africa discussing possibilities of a flagship program in quantum hardware and thinking about which approach. And we had a few people, quite a number of people in the photonics, and made a strong argument in terms of costs and a lot of other considerations. What would be your recommendation? Not biased towards photonics, but is it something that an approach that you think, if we are considering doing this flagship program, experimental flagship program where we bring together scientists from different places to work on this? Is this an approach that you will recommend for us?
Well, it's an important question, and you'll know, of course, that other countries are thinking of these benchmark initiatives. The DARPA program, QBI, in the US has put, I think, 20 companies into phase 2, including some photonic companies. And the UK NQCC benchmark program also has a neutral atom ion superconducting and photonic platform in it. Look, I would say at the moment the jury's still a bit out on which of those hardware systems is going to really be scalable. Every single one of them has some fierce technology challenges, including photonics. Currently, if you ask, well, where is the most advanced photonic hardware? It could well be in SciQ or Xanadu, probably SciQ. But their approach is to put everything in a cryostat. So in that sense, you're not any better off using that than using a superconducting machine, because you've got many of the same problems. So I think it depends what you want to do. I would be wary of trying to pick a scalable, fault-tolerant platform at the moment. But I do think, as I've tried to illustrate here, that if you're interested in some of these hybrid algorithms where sampling is an important part, I think photonics has a very powerful role to play. And a bit that I didn't talk about, but I think it's also got a very promising role in direct quantum machine learning, where you build a fully quantum neural net out of optical components. And that whilst it may not be universal, I think is going to have quite a lot of applications. Not sure if that answered your question, Prince. I'm not sure I can tell you how to spend your money there.
Okay, thank you very much. Thank you. We are on time, but half an hour late because we started half an hour late. Lunch is at AIMS, so the shuttles and buses are ready to take all of us to lunch. And then from there, you can get started in your groups. So for those of us who are going to the workshop at the Google AI Lab, the shuttles will be there to take us from AIMS to the lab. So thank you very much to everyone, and we wish you a successful hack. Thank you. Okay, before we go, let's have a group picture on the stage. If we can all come up on the stage.
The speakers and judges. Hello? Yes, please, the speakers and judges will be down, and then the rest of us, please, let's climb up the stage so that we can take this picture together. All our speakers, our judges, and then our mentors. You can stay down, and then the rest of us will climb the